that's a mouthful. Really, it's an exceptional workshop and an exceptional project. Resource Project has gone from making the Raptor, the very big sorting machine, looking at refractory materials that you can see on the picture, on the initial slide, and loads of technology and data science behind that, to looking at characterization of materials, to now looking at alternate applications. So you'll keep an open mind during the course of the presentations. Don't assume it's just heavy industry related. This workshop I'm from automotive, and it can be used, especially with some of the challenges that we have with EV and temperatures across the engine base and motors. So this morning you'll hear from RHIM, so they're the lead industrial partner. You'll hear from CPI, who are an RTO based in the UK, and you'll hear from Crowd Helix. And you'll hear lots of different elements that this project has given us the opportunity to look at. So I'm going to hand you over to Alexander Lettner, who will take us through an overview of the project and of the workshop. Thank you, Alex.
Thank you very much, Claire, for this nice introduction, and also welcome from my side. So my name is Alexander Leitner. I'm working for RHI Magnesita, and I'm also technical coordinator of the resource program. So what I would like to do is to give you a little bit of an overview at first, what you have to expect here from this workshop today. Can we move on to the next slide, please, Ananda? So just as a basic idea, what you will gain, we will start with an introduction here. At first, a little bit on refractories themselves, so that you also understand what's actually the origin of the material we are talking about. I would like to show you a little bit the sustainability perspective of how this is impacting like also society at the end of the day. Then when we go on, next part will then be done as mentioned by CPI. We will talk a little bit about materials, what are their properties and how have they been characterized. And they will also outline a little bit possible applications we have here within that, right? So all of that should at the end really serve as a base for potential collaborations. But now I think we would like to start with a short interactive session. So we have prepared here a short Menti where we would like to get a little bit deeper into the field of refractories themselves. So on the next slide, you are going to see there the QR code, and I'm going to take over control here. So will be 10 questions, I think, and yeah, there will be a small surprise prize also for the winner. See here. So yeah, please use the QR code there. I will just wait for 1 or 2 minutes until people have joined. Move on. Okay. Yeah, the reason we do that is that usually refractory industry is a quite hidden industry, right? It's B2B, so mainly serving to other big industries. And there is usually not so much knowledge about it. That's why we prepared here a couple of questions. Okay, I would say let's try to start. We can still find this code up there in case you have not managed yet to be there. But I would like to start with the first question, which is actually what does the term refractory refer to in material science? Is it materials that reflect infrared radiation? Is it materials that dissolve in water? Are those materials that retain mechanical strength of up to even more than 1000 degrees C? Or is it materials that conduct electricity? I hope everybody is able to vote. I see that here some 2 more answers are missing at the moment. Seems like 1 answer is still missing, but we can also give it a try and see. Good. So I think the 7 of you are, of course, completely right. We see that was the right answer. Usually, sorry. That's how it should be. Good. Then we are going to move on with the next question, right? This means, which of the following is a critical requirement for a material to qualify as refractory? So this is the lightweight structure and UV stability. Is it high electrical conductivity? Is it transparency and low melting point? Or is it the ability to maintain thermal stability and chemical resistant and under extreme conditions and temperatures? So we've now hidden the answer, so it might get a bit harder, not just people selecting the same thing. Yeah, let us see what's the correct answer here. It's the ability also to maintain thermal stability, chemical resistance under extreme temperature, right? So it's not only about the melting point itself, it also needs really to fit to the customer process, because otherwise it will not serve the purpose of protecting customers' aggregate against the media which is processed in there. Okay, good. Next question. Which of the following materials is not typically used in refractory production? Is it either silica, alumina, or magnesia, or polyvinyl chloride? Okay, again, we have 7 answers. Let me see what are the responses. So 2 are saying silica, which is not the case. So actually, really, polyvinyl chloride is the one which is not resisting high temperatures, right? Silica has also melting point of more than 1000 degrees C and can be used in certain applications. Good. Let's move on to the next question. In which of the following industries are refractory materials critical? Is this steel, cement, glass, non-ferrous metallurgy, waste incineration, chemical industry? Does this rather belong to data centers, wind energy and air conditioning, or to food packaging, agriculture and carbon fiber production, or textile dyeing, refining, or furniture coating? Good. People are really quick now. So we can see, yeah, all of you guessed right. So it's really related to material production where very high temperatures are used. Good. Now getting a bit closer to the context of sustainability, right? What do you think is actually the average CO2 emission per 1 ton of refractory product which is produced by RHI Magnesita? Is this 0.16 tons? Is it 1.6 tons? Is it 0.06 tons? Or is it 6.1 ton? As a reference, right? So like the average CO2 footprint of a citizen in Europe is roughly 6 tons per year. Oh, we need some more answers. Okay, let us see what's the choice here. And that's correct, right? So 7 people choose 1.6 tons per ton of refractory product. So please also just consider that, right? That means that we are actually producing in terms of mass more CO2 than we actually produce as a refractory material to be used after that. So this is quite a significant impact, of course, we have here. Good. Then the question is actually, where does this come from, or where does this, why do we have so many refractory products? Is the main impact coming here from water used during shaping and drying of materials? Is it local transportation from warehouse and raw materials to customer and manufacturing facilities? Are these the fossil fuels used in production? Or is it actually the raw material and the processing, which is called calcination itself? Perfect. We have the responses coming in here showing you. Okay, yeah, that's probably a more not so known fact, right? Actually, we use a lot of fossil fuels and we also need to produce our materials at high temperatures. But indeed, it's actually the calcination of the raw materials. Yeah, so that means we are having usually carbonates as a raw material, which has intrinsic CO2 stored. So we have really a raw material topic here regarding sustainability. Okay, then two more questions. So what do you think? How much recycling is used in refractory products at the global scale? So not talking only for alkyl magnesita now, but really on the global production. Are we using 60% in our products? Are we using 3 to 5%? Are we using around 80%? Or are we using less than 1% in our products? Okay. Good. Of them are there. So unfortunately, it's not over 60%. That has different reasons, which I will explain to you a little bit later. The correct answer is that on a global scale, there's only 3 to 5% of this material used there, even though it has such a high carbon to footprint. And we are at RHI Magnesita very proud that we are having a recycling rate close to 15%. So we are here really front runner in this field. However, it's quite challenging to really further increase this number. That's also something I would like to show you in the next few slides. Good. Also to get a little bit of an idea of the scale, right? So what do you think, how many tons of spent refractories are actually generated worldwide each year? Yeah, I mean, not very easy to get the very solid numbers here, but there are a couple of publications out there. So are we talking about 3 million tons, 120 million tons, 28 million tons, or 320,000 tons at the global scale? Good. Let's see what's the result here. Okay. The right answer is 28 million tons, right? So we talk a very significant industry in terms of material volumes. Yeah. So there is a lot of material out there, and it's of course also a big issue that not more of this material is recycled in a good way on a global scale. Good. Last but not least, turning a bit to the project. So what do you think that actually the resource project we are talking today about is making it so unique? Is it building new primary mining infrastructure in Europe? Does it focus on replacing refractories with plastics? Does it export used refractories to landfill sites somewhere abroad? Or does it aim to sort currently unsortable materials? I think this will be an easy one. Good, waiting for one or two more replies. And well, I think it should be clear, hopefully. Yeah, it aims to sort currently unsortable materials, right? So that means a lot of these spent refractories out there are, for different reasons, not very easy to reuse. And that's exactly why we need also technology and new processes in order to get better here. Okay. Good. Maybe I'm going to switch to this presentation directly now. Okay. And I would like now to give you a bit more context. Regarding the ranking and the price, I will come back to you at the end of the presentation because I can now see in the results of who got most of the right answers. Okay. Can you see my screen? I hope it should work. Okay, yeah, I already talked a little bit about refractories, right? Those are really materials which are protecting customer processes where we need very high temperatures, right? So here for you to get just a basic idea of where refractories are used is, for instance, steel industry, right? So per ton of steel, we also need to use 10 to 15 kilogram of refractories. But it's also about copper industry, concrete production, cement production, of course, more in that relation, steel production, glass, aluminium. So I think with almost all materials you're in touch with every day, refractories are one of the very essential parts which are needed to be produced. For that, we use three main raw materials, I would say. The first one is MgO with a high melting point of roughly 2800 degrees C. Then for lower melting point applications, we also have alumina, which is close to 2000 degrees C, and then silica more in the range of 1500 degrees C. Yeah, and what I've mentioned before is already that, of course, if we are now using recycling instead of primary raw materials, that gives us an enormous benefit in terms of CO2 savings. Means for every ton of recycling used, we can save roughly 1.5 ton of CO2 in our production. So, however, the refractory world is quite complex, I would say. So we have very different product solutions. Here on the right-hand side, you see an overview of the material systems we are using, right? So usually we are not using just pure systems with one raw material, but also products where we are mixing different constituents. This can either be then produced as a brick. Yeah, it's a bit like building a house. You have certain bricks you put on top of each other in a certain aggregate, classical bricklaying. We also have products which are called monolithics and precast, so that's more similar to concrete, right? We have here mixes delivered and on site at the customer that will be mixed with water and so water or other solutions and can then be hardened on site at the customer and dried. We can also precast that, and then we also have a couple of products which are called functional products. Means they're not just there for resisting these very harsh conditions, but they also have a very active functional purpose. For instance, in controlling the flow of a steel ladle or so on, or having purging. Yeah, but take home message is here that it's quite complex and that we are having a lot of different materials. Yeah, that's just a little bit highlighting again of where actually we are having our high carbon footprint, right? One of the main raw materials used, I mentioned, is magnesium oxide, and what's mined is magnesium carbonate. So that means if you would like to produce MgO, you need to heat that at a very high temperature, and you will release CO2, which comes out of this so-called raw material magnesite. Yeah, and very hard to prevent. However, of course, if you go through the full circle here, you do your product is used within the customer, and it's then getting recycled. Of course, we are not entering in the primary raw material production cycle anymore, right? So we will be really getting rid of the CO2 emissions we have here during calcination, and that's exactly the reason why we have this very high benefit in terms of CO2 savings when recycling is used. So I think we can agree that recycling is a very nice thing, but actually, why is it so difficult now for refractories? Yeah? What you can see here on the left-hand side is the aggregate which is used here in steel production. It's a blast oxygen furnace, which is lined with material which, from an optical point of view, looks quite similar. However, if we look inside and you see here a lot of different colors, those are referring to different product and different product qualities, right? So that means they might have a different chemistry and so on. And this is really needed because inside of this aggregate, we have very different, actually very different areas in terms of the conditions they have to withstand. Yeah, can be some impact here, can be more aggressive in the slack zone and so on. And what happens actually after service is that all of these products are usually getting mixed up, as you can see here, yeah? Because that needs to be a fast process that's happening in the environment of a steel plant. So it's not really a possibility to take them out brick by brick. Yeah? So what you end up with is like this big pile of unsorted material now, which on top are not looking like what it looked like when we put it in there, right? So there will be some infiltration, there's some impact from the customer process and so on. So it's actually a very diverse pool of materials we are getting back. So how can we overcome that now? I think it's very essential for us that we are able to really automate sensor-based sorting. Yeah, and these are several reasons. Nowadays, still the state of the art across all regions in the world is actually hand sorting. So that means there are really people on a conveyor belt looking at the bricks and judging in terms of different characteristics. Can be visual one, can also be a little bit on the shapes of the edges, for instance, and other features, right? So they're like making a lot of decisions every day, but it's not really recorded on what these decisions are based on because it's like really, it's a sum of a lot of different characteristics they're looking on. Yeah. And now, of course, with automated sensor-based sorting, we allow for gathering much more data. So what we are doing here is what we already currently do actually is we have combined laser-induced breakdown spectroscopy. That's one part of the process where we have a laser shooting on the material. There you will see a spark emerging like here. And from the color of the spark, we can learn a lot about the elemental chemistry. We're also adding here hyperspectral imaging, right? So that's a very specific camera, which gives us more of a clue also in mineral phases and mineral phase composition of the material. And with a lot of data received from both of them, we apply artificial intelligence algorithms here to have really optimized solution, right? And that's what we call our Raptor. This is the fully automated refractory recycling equipment. Just to show you a little bit what it's looking like. Here are short image videos of our project. You will see here the different spent refractories on the belt, which are here measured by the laser. You see this is a very fast measurement, which is important because we are having high volumes to sort and produce. So the information of the spark will get into the computer, will be measured by the hyperspectral imaging camera, and then we can either use pick and place robots here to put them in up to 8 different classes, or at the end, there's also the possibility, especially for small particles, to differentiate them into different sorting classes also by air rejection. Yeah, that's a bit of a glimpse on this machine, which is now already up and running in one of our recycling centers. And yeah, I would say with really fully changing this process, one thing is, of course, also that we are not just receiving the very same material streams as we used to with the manual sorting. So that means we are coming up here with new materials, but also with some streams which might not be directly reusable in the refractory industry anymore. That's actually where our partner here, CPI, comes in. And at this point, I would also like to hand over back to Ananda, who will give you now with his team some more information on some specific materials we are dealing with and which have been characterized over the last few weeks and months. Okay, thank you very much. Ananda, I would hand over to you at this point.
Thank you. Thanks, Alex. It was really very interesting to get that introduction from you, and the Menti quiz was equally interesting as well. Can you share? Can you see my presentation?
Yes.
Thank you. Thank you. We CPI as a team, as you can see here, we looked into the alternative application of these spent refractory materials as we got them in the size fraction of 0 to 5 millimeter. So in the next few slides, we will be talking about basically on three things. One is the material passport. The material passport is a fingerprint description of these materials, of these waste spent refractory materials. We will also talk a little about the low energy intensive and most economical way to further process these materials, as using it with a polymer matrix in a polymer composite. 0 to 5 millimeter is not always a direct introduction. We have to reduce the size further. And also at the same time, finally, we will talk about, we will give you some understanding about the material properties when these materials are mixed in a polymer matrix to form a polymer composite, and especially focusing its usage in the area of building and infrastructure and also in automotive sector. So I'm handing over to the presentation, the next sort of slides to my colleague Jack. Jack will talk about the characterization of these materials and how we come to a material passport finally. Over to you, Jack.
Thanks, Ananda. So, as Ananda mentioned, these materials are spent refractory materials. And so the first thing that we decided to do was undertake a kind of characterization of what these materials are and how they behave. So we started by looking at the chemical composition of these materials. And we used a range of our different techniques that we have. So looking at XRD, FTIR, EDX, and Raman, where we can really look at what phases are present, what bonds are present, and what elements are present in these materials. We have a typical composition of the brick class for both this RefSem material and the RefFerro material. And they differ slightly. So the RefSem material has got slightly more calcium species in, whilst the RefFerro material is a bit simpler with magnesium oxide, graphite, and spinel. Generally, across our different characterization techniques, we see the materials present that we would expect from the initial composition of the brick class. We then had a look at the particle size distribution and the density of these materials. So although there are 0 to 5 millimeter size fraction, we didn't know how the particle size distribution would vary across that range. And we actually see that both of these materials have a bimodal size distribution with size classes kind of dominant at around 53 to 200 microns and 1700 to 3,500 microns. The bulk density of both materials is fairly similar, 1.7 for the RefSem material and 1.6 for the RefFerro material. And the skeletal densities again are then 3.2 for the RefSem material, 3.1 for the RefFerro material. The difference in the bulk density and the skeletal density is due to the voids that are present when you measure the bulk density. We also had a look at the physical characteristics of these materials, whether or not they have interesting magnetic properties, dielectric properties, and electrical properties, and thermal conductivity properties. What we see is that really the interesting properties are perhaps that the RefSem material behaves as a dielectric and an electrical insulator, whilst the RefFerro material behaves as an inductor and an electrical conductor material. And the reason for that is that there's a higher amount of graphite present in the RefFerro material, so we can form conductive pathways to create that electrical conductivity in the material. Both materials are also thermally insulators, which is what we'd expect given that the applications that these materials have been used in. So the materials were of a 0 to 5 millimeter size class, and we realized that for certain applications we might need to do some processing and change the size class of these materials to an appropriate size for the specific applications. So a lot of the applications we've looked at are using these materials in polymer composites, where we need a D50 that's below 10 microns. So to achieve that, we did some milling. We did lab scale milling, looking at kind of 20 gram scale. And then we upscaled this to a multi-kilogram scale. And we managed to achieve D90 below 10 microns. But due to how we process these materials, so we do a wet milling process, we see some change of the materials from magnesium oxide to magnesium hydroxide. We get some slight changes in the properties in the materials with this change. So a slight reduction in the skeletal density. But actually, magnesium hydroxide is potentially quite an interesting material for fire retardant properties. We then characterized these milled materials and have produced material passports for both of the materials. So we again looked at the kind of particle size distribution, the densities, the surface area of these materials, and the surface energy of these materials. We have a look at the MREF Chem, which is a nice kind of cream color, and the MREF Ferro, which is a gray color. And both of these material passports are available on the resource project website. So both of these materials have a reasonably high surface energy. So we can also modify the surfaces to enable better integration into whatever application we want to use these materials in. So the model surface modification that we've looked at here uses silanes to treat the surface of the material. And we can create certain groups, certain functional groups on the material surface that allow it to react into whatever network we want. So for instance, here we've looked at treating the material with a silane called Glymo, which has an epoxy group on it, so it allows it to react well into epoxy systems. We can see that we can modify the surface energy of the materials here by changing the amount of Glymo that we've used to modify the surface. But whether or not we need to modify the surface really depends on the exact application that we're looking at. So we have an example here on the left where we're putting it into an epoxy system, and really the treatment of the surface makes very little difference. Whereas on the right, we have an application where we've put this into a dielectric ink, and actually the treatment of the materials really does improve the properties compared to the untreated materials. I'll now pass on to my colleague Hugo, who will talk in more detail about some of the applications that we've looked at.
Thank you, Jack. So just to recap on that and on the theme of application, so what my colleague presented was the foundational work for the potential application space for this material. So ideally, as Ananda also mentioned, we would probably like to use this material in its received form, but with the hope of maintaining the control and desired performance outcomes, but that's not possible. And to ensure consistent results, that's what Jack has also mentioned about, including the material passport and also establishing those standard preparation protocols. But also the importance of surface treatments according to how you can get this material's functionality for specific applications as well. So in the further next slide, set of slides, what I'll try to showcase is the performance of this material and also assess its suitability and validity across different scenarios of these applications. And starting with initially with the burning test of these materials, which we used as a standard within a standard epoxy. So as global fire regulations continue to tighten up, there's a growing demand for these non-halogenated or low toxicity flame retardants. Refractory materials, as a matter of fact, can withstand very high, extremely high temperatures, and it shows those characteristics of making them as potential candidates as a functional fillers to perform within this fire-safe polymer composites. So in this case, we'll try to evaluate the fire performance of the epoxy composites, trying to incorporate these two refractory waste-derived fillers of M-Ferro and M-Chem, and compare their effectiveness with that of a conventional benchmark of the flame retardant of aluminum trihydrate. So basically, the burning testing was conducted by a cone calorimetry test with a equal percentage loading within the epoxy. As you can see on the right-hand side of the graph, that the ATH actually outperforms both the MREF-Chem and the MREF-Ferro materials. A gradual improve can be seen with the MREF-Chem, but not a lot of pronounced sort of like heating, thermal shielding that can be observed within this sector. But where the opportunity lies within this advantage of this waste fillers is within the HRR or the heat release rate and the toxic gas release. So as you can observe, the epoxy system has a very high and sustained HRR or the heat release rate, but the ATH also has the same sort of properties with which you can observe over there. But within the materials of the MREF-Chem and the MREF-Ferro composite, you can see a sustainably sort of reduced peak heat release is observed, also indicating that the suppression of this combustion reaction is taking place. But more as acting as a physical barrier for toxic gases such as carbon monoxide, carbon dioxide, you can see the same sort of behavior which you can observe within the epoxy and the ATH as well. And you can see the amount of CO and the CO2 release within the MREF-Chem and MREF-Ferro is much more lower. So such behavior is quite advantageous within the construction materials. So therefore, helping to delay that spread, which is critical for evacuation and firefighting, but also the fact that the harmful gases that has been released within the burning system is very advantageous to be used as well. So I would like to sort of move on to more into complex situation in terms of the polymer composites, especially looking into the application within the thermoset and thermoplastic composites. Now, as you will be aware, there is a wide range of industry and of thermoplastic and thermosets within the industry, and these are very much attractive due to its diverse sort of properties. The use of fillers are very enhanced and very knowledgeable as well within this field. But what we'll try to do now is try to look into the effect of these fillers within this thermoset and thermoplastic materials, and also compare their effectiveness to conventional benchmark fillers as well. So firstly, we would like to start with the epoxy-based thermoset composite. So looking into the thermoset functionality of this fillers within the epoxy composites, especially looking into their thermomechanical wear, thermal and electrical properties. As you can see with this slide, the enhancement, especially in the storage modulus, is quite higher in terms of the calcite on the first graph within the storage modulus. And it outperforms both the untreated and surface treated sort of MREF-based fillers. But the advantages of this impressiveness is sort of like an application based, depending on what is required within the thermoset sort of like context. Thermogravity analysis shows there's a much more thermostability with the addition of these fillers. But looking into things like wear rate is much quite exciting to see that, you know, the epoxy based on its own doesn't wear a lot, but you can see with the inclusion of calcite and MREF came a lot more wear rate happens, but then MREF ferro sort of like withstand that wear rate within the system. And then, as my fellow colleague Jack also mentioned about the different thermal and the electrical properties, you can see that it kind of follows the same sort of like properties as we did observe with the initial raw materials in itself. Now, moving on to the thermoplastic-based composites. So there is a whole wide of ranges that you can use, but we have tried to withstand ourselves with the use of high density polyethylene and also polypropylene within these thermoplastic ranges. And we have tried to identify the optimal filler loadings, looking into its stability and its thermal performance as well. So firstly, looking into the virgin high density polyethylene, you can see out there that there is a lot of work that we have done over this vast period. And depending on the nature of your material itself, depends on the application purpose as well. So for example, with the TGA, it is quite substantial to see that there's a trend of increasing residue with higher filler content that is quite observant with all of the fillers that you can see. The MREF ferro that basically especially shows a very high inorganic contact. So basically mentioning that it has a much more better, higher thermal stability. On the right-hand side, where you can see the DSC or the thermal behavior of these materials within this thermoplastic of high-density polyethylene, you can see there's a quite increase on the both melting and crystallization temperature, especially for the MREF ferro material, indicating that the MREF ferro as a promising candidate for application requiring high stiffness, dimension stability, or thermal resistance as well. But with the inclusion of calcium carbonate and MREF ferro, minimum influence can be observed within the thermal transition. Moving further, looking into the mechanical thermal analysis of this material within a different temperature sweep, especially what we have looked into this, the storage modulus basically looked on the different temperature regime. Now, one of the trend that we can basically observe is that with increasing temperature, the storage modulus decreases. Now, this is very typical of the thermoplastic behavior. Basically, with increasing temperature, you can see the softening and reduction in the mechanical rigidity. But you can see with the inclusion of these fillers within the system that, especially with increasing filler loading, that there is an increase in their stability. And then with up to 40% loading, that the storage modulus is much more higher, especially for the MREF ferro material system. Therefore, all of the systems evaluated states that MREF ferro provides a much more significant reinforcement within this polymer system of high-density polyethylene, making it a very strong candidate for application requiring enhanced load-bearing capacity or performance under elevated temperatures. Last but not the least, within the polypropylene system, we tried to include this fillers and see its performance again within the same structure of the mechanical or thermal establishment. And as you can see with the viscosity graph over there, it's quite substantial that the MREF ferro especially shows a very sharp increase in this viscosity, almost 3 times the other fillers within the system. The pronounced rheological reference of the MREF ferro filled composite highlights that its potential as a reinforcement agent is again very high, with higher melting strength and also dimension stability, which is required within the polypropylene system. So it enhances those systems within the composites of the polypropylene. It is quite substantial. Again, looking into the mechanical properties of this thermoplastic of polypropylene. Firstly, the flexure modulus is not affected very highly. So basically, the stiffness remains very similar. But then you can see that ductility within the MREF chem is increased within the stain to break, as you can see with this testing. But one of the things that would be highlighted over here is the tensile Young modulus, especially as you can see the MREF ferro within the graph stands out very much. Also compared with the alternative fillers of calcium carbonate, that the MREF chem also stands out a bit. So therefore, again, sort of like proving the concept that MREF ferro, MREF chem provides that stiffness within the system, and giving some sort of a property indication with the application of these fillers within the system. Now, there was a lot to sort of like cover within the application base, but we have only reached out to what we thought was appropriate within the system. But you can see as a conclusion that MREF ferro and MREF chem within the commercial epoxy base shows reasonable properties for replacing the standard filler of calcite that we have used to show that comparability. Furthermore, MREF ferro makes a stronger the composite much more stronger and much more heat resistant, which is ideal for tough, long-lasting products. MREF chem has a good mix of strength and flexibility, and it's much more easier to process during the manufacturing of these polymer systems. But both of them are as good or even better with the regular fillers of calcium carbonate, which is proven within this study we have undertaken. So basically using these recycled fillers to help reduce waste, cut carbon emissions, and also support the circular economy stands out very much pleasantly within these systems, and gives further opportunity to look into more specific application that has been that could be considered with the use of this material. And also it shows a very promising way to turn industrial waste into valuable new materials. So I think that is from our side. So maybe someone from Crowd Helix is over here to talk about it.
Yeah.
Before we move to Crowd Helix, I just would like to pause and give the opportunity for anyone to ask questions of the technical team. Please feel free, raise as many questions, and a copy of the slides will be available and the data information pack. So don't worry if you have lots of technical information that you didn't catch in that presentation. Do we have any questions?
I have a question.
Mm-hmm.
So how long are these composite materials expected to last in building applications?
Would the CPI technical team be able to respond?
Yes.
Sure. So we've not done any testing for how long they might last, partly because we have the capability to do this testing, but really what we want to do is find specific applications that people might be interested in, and then do testing that's most relevant to that application. So if anyone in the call has an interest and a product that they really think they could use these materials in, then we want to work with them to test in ways that are relevant to their specific application, using the capabilities that we have.
Okay, so it's varied depending on the application's use and performance requirements.
Yeah, but CPI has got the capability of accelerated weathering test if you are specifically looking into that. So just to mention that in this forum.
Thank you. Are there any additional questions?
I have one more question. Which specific areas or components within the building sector do you see as most suitable for the application of these composite materials?
I think it again it will vary. If you see Jack's presentation, or sorry, Jugal, when he presented, he shown a kind of a epoxy-based tile. So these type of materials in combination with a polymer matrix can be a very good candidate for roofing tiles probably. And due to its very low thermal conductivity, it can save a lot of energy. So these type of products in combination with a polymeric matrix can be a good candidate for roofing tiles. Having said that, it can also be used in very many other areas for building an infrastructure. We are working with other companies. I cannot take the name, unfortunately, but we are working with companies who makes some internal, roofing solutions, and they are using this material as a direct replacement of the traditional fillers which they use, and also for texturing purpose. So these materials, but if you have a specific requirement, these materials needs to be checked for fire testing to be a good candidate for use in building an infrastructure. But I gave just two examples. It can be used externally as a roofing tile, or it can be used in specific internal areas. If that answers your question.
To expand on that, Sophia, some of the other applications where we're in dialogue with companies within loads of sectors, not just the building and infrastructure. We're talking with companies on road surfacing, on machine plastic parts, so that where you need the thermal properties, PEMD, which is power machines, electronics machines and drives, predominantly in automotive, and that's because of the EV and the thermal properties that are generated around the battery. We're talking with companies on facades on buildings. In the UK, there was a historic issue of Grenfell, and that was a very serious fire based on a facade of a building. And so companies are very interested. It's politically and socially very sensitive in the UK at the moment. We have flooring, internal flooring, and looking at the wear properties. Heavy duty plastics and wind turbine blades. So that's just a cross sector of different applications that we are in open discussions with companies on. So hopefully that helps set the varied capabilities of the material.
Just to add, also in this, these type of materials can also be used in cement and concrete type of those areas. This is not a part of this webinar, but we have a webinar coming in the mid of July, where we will focus specifically on concrete, on cement as an additive, as a sustainable additive on those specific areas.
So in conclusion, there's lots of different product applications that we can use. CPI, as part of our close out of the project, will look at trying to give technical support. So don't think, oh, I wonder if it would work. I'm not sure if it would work for my application or for my product. The technical team can support you by looking at the characterization of your material with this material as a filler. We can look at the theoretical performance. We can do some mechanical testing of properties. So that there's a whole myriad of capabilities whilst this project is still running that we can give you to support the barriers to use of the material. We also have Jack presenting at the 17th International Materials Conference in Edinburgh on between the 7th and 10th of July. So please feel free to go across and speak to him. And in an automotive context, we will be having a stand at the Northeast Automotive Expo because we're talking to quite a lot of the automotive tier 1 players. And obviously Nissan is the NMUK, is the in-region OEM. So please feel free to come across and meet us there. Thank you so much for your time, and we will issue you a copy of the presentation. Thank you.
Thank you.